A very good morning to all of you. While we are talking about normal regulating or operational ancillary services, the objective of this presentation is to throw some light on emerging ancillary services, so looking a bit beyond the normal ancillary services. This is the outline of the presentation. I will talk about a little bit about variability of wind, then impact of wind on system inertia, and on the grid security, as well as voltage stability, and finally I will talk about one of the emerging issue with high penetration of wind. This is just a brief about wind turbines. I wanted this slide primarily because of this wind farm, wind turbine 1 megawatt in Denmark, which is one of the oldest wind turbine in operation at the moment. This wind turbine was not built up by any commercial company, rather it was a community that came together and built up this 1 megawatt. It was then the highest capacity wind turbine of the time in 1975 or so. So we are here with the modern wind turbine technology. I think this graph you might have seen quite a time, so I'll skip this. I will try to go to this slide. This is an interactive map that GWEC has published. You can see how wind energy has evolved over the time. This red circle is showing showing India, and beside this huge bulge is China, 170 gigawatt coming as of 2016. So there is rapid growth of wind, as we all know, and India is at number 4 in terms of the capacity, installed capacity. I will touch mainly on the technical issues and related emerging ancillary services. One, as we all know, is variable in nature, this wind or solar, and ramping has been talked many a times during this conference during the past 2 days. And then I will talk more about this wind-driven displacement of conventional synchronous plants, how it results in low synchronous inertia and diminishing sources of frequency operating, conventional frequency operating reserves, short circuit power and reactive power, primarily dynamic reactive power, and then post-fault delayed active power recovery is one of the emerging issue with large-scale wind penetration. So if you see on the plot on the right side, this is from Germany, 50 Hertz. You can see how the variability is there in the system, and how much the grid has to actually adopt its flexibility level to accommodate this variable generation. On the left side is a typical demand curve, load curve from India. If you see towards the evening peak, if we talk of 2020 or beyond, this ramping down of solar will sort of coincide with ramping up of load, which is one of the worst case, and the ramp requirement is expected to reach probably beyond 30 gigawatt per hour. That's one of the reason of this because of the solar that's increasing dramatically this ramp rate. But with beyond that, there will be intra-hour or intra-unit commitment time slot, this variability that we are talking quite often, which needs to be tackled with a large share of renewables. These are some of the plots from the two states of India, Maharashtra and Gujarat, showing how the wind is varying over different months of the year, and tries to highlight the necessity of the ramping capability of the system. So let's talk a little bit about the system inertia under high penetration of renewables. If you see the plot on the left top, it shows the increasing percentage of non-synchronous generation for the same outage of a plant, how the frequency dip is increasing with the increase in the penetration level because of the diminishing system inertia. As we displace conventional power plants, the inertia, that rotating mass also goes out of the grid, and the inertia also decreases. The system inertia also decreases as a result. Because of low system inertia, the rate of change of frequency goes high, and the nadir point also, that is the minimum frequency point, also goes high for the same outage of the generation in the same system with different levels of inertia. If you see the plot on the right top, this is a study done by Irish TSO, Airgrid, and Sony, that's Northern Ireland TSO. It shows that the system for 2020 is going to be, as per this study, in 2020 the system is expected to be insecure due to the lack of sufficient adequate system inertia for around 30% of the time of the year. So it sort of highlights the importance of maintaining this adequate system inertia. The two impacts of this system, this inertia, is one is for the same generation outage, the minimum frequency is going to be quite low and probably cross the under frequency load shedding and beyond that. One is that. The second important point to highlight here is rate of change of frequency. The rate of change of frequency relays that are there in the conventional generators or distribution systems for anti-islanding operation. If we have low system inertia, this rock-off rate of change of frequency is going to increase, and that is probably in some worst cases going to activate those rock-off relays of the generators or the distribution systems. While we talk of this emulated inertia, quite often that wind can provide emulated inertia. I want to highlight 2 points here regarding that emulated inertia from wind. One is the rock-off relays in the system are going to operate based on the maximum rock-off that we see during the event. And that maximum rock-off rate of change of frequency is going to happen at the very instant of the event. That's at the very beginning. And this emulated inertia is not going to come into picture at that very instant. It is a bit delayed. That's only these synchronous inertia with the synchronous power plants that instantly comes into picture at the instant of the event. So this maximum rock-off, that is initial rock-off of the system, is still a bit of issue that we need to look at how to compensate it, and probably down the line in some cases, in some countries, it might arise, the need might arise that we should have some minimum synchronous inertia rather than only non-synchronous inertia. So the rock-off is very important. Anti-islanding, if the anti-islanding of the distribution system is active, gets activated because of the event, it will lead even to the outage of a bulk wind generation or the distributed generation that is going to increase the issue further. One more point I would like to highlight here is, while wind turbine can provide emulated inertia, but we need to be cautious about the aggregate impact or aggregate effect of this emulated inertia from wind. The plot on the right bottom side shows different curves. One is no emulated inertia. There is no emulated inertia. It is the study on the Irish power system. No emulated inertia in the system, and of course the frequency goes down and it settles down at some point. Then the red one is showing emulated inertia response from wind. So every wind turbine, whichever is capable of providing emulated inertia, it is providing inertia to the frequency event, to the outage of a power plant, and the nadir point is improved, as you can see here. But the issue is that this inertia comes at the cost of decreasing the speed of the wind turbine. So once this event goes, this nadir point goes, the speed of the wind turbine starts picking up. As a result, the net power output from the wind turbine goes down, or in other words, it draws some additional power from the grid to regain its speed. So if all the wind turbines operate with the same setting of the inertia, and they provide inertial response in aggregate, and then they draw additional power while recovering back to the normal speed again, draw additional power from the grid, that additional power in some cases may result in the next frequency dip in the grid. So a proper coordination or probably some distributed dispatch of the inertia, fast dispatch of the inertia might need to be taken into account while thinking of the aggregate response of the emulated inertia from the wind. This is the study I was involved in on Danish power system. This was done in collaboration with Danish TSO. If you see the plot, both studies are related. If you see the plot on the left side, this is Danish power system planned for 2030. We try to see with the existing infrastructure how the system is going to behave down the line with higher penetration of wind. This is the fault at 400 kV substation, Vester Hassing substation in Western Denmark. If you see the voltage due to the lack of adequate dynamic reactive power in the system and short circuit capacity in the system, the voltage is not recovering fully to the nominal value following the fault clearance. And in the initial few seconds, what is actually happening is distributed combined heat and power plants whose primary product is heat, not electricity. They are not bound to follow the normal grid codes. So they are allowed to have simple on and off operation depending on if there is a disturbance in the grid. So in the first few seconds, what is happening is as the voltage, there is a delay in the voltage recovery, those distributed CHPs back off from the system. So what happens, it actually aggravates the situation, and then following that there are significant penetration of old wind turbines type 1 and type 2. Again, they are allowed to have on and off operation in the system. So following the outage of these distributed CHPs, there was the outage of those old turbine technologies, and that led to the outage of further delay in the recovery of the voltage, and then outage of type 3 and type 4 wind power plants, and finally resulted in the collapse of the system. This is one of the worst case that I have shown here in the presentation. And on the right side, if you see, this is trying to show the security plot of the system with CHP, that's combined heat and power plant, central power plants, and wind penetration. As we see, so this is the security level is measured both on the transient stability as well as the voltage stability. As we go higher in the wind penetration, it shows that the security level of the system is going significantly down until and unless there are some remedial actions taken into account. So it was just to try to see how the system is going to behave. Again, we didn't consider the countermeasures that Dynasty TSO is going to take into account down the line. It was only to check the limits of the system and highlight some of the important issues here. Short circuit power is very important here. While we talk that these wind power plants or solar power plants can support the dynamic reactive power, no doubt in that, but they have the limitation of providing the adequate short circuit power to the grid, which the conventional power plants have the capability. So Danish TSO was actually trying to address this lack of dynamic reactive power and short circuit capacity by having Mustown power plants in the system, but it was not a cost-effective solution. So what they ended up doing is having synchronous condensers installed in the system to get away with this requirement of Mustown power plants. But there are other countries who also have the requirement of this Mustown power plants. For example, Ireland, I guess it is still in place. They also have the requirement of Mustown power plants for the security of the system. I'm just going to skip this slide for the interest of the time. So I will briefly talk about one of the emerging issue with this high penetration of wind. If you see this chart here on the right side, I think it will be better to understand it from the right side. So if there is a fault, there is a voltage dip in the system, and the next plot with the voltage dip in the system, along with the generation output, fall in the generation output, the load also decreases because of the change because of the decrease in the voltage. But in the conventional system, as the fault is cleared, voltage quickly recovers back, the generation recovers back, and load follows the suit. So the generation and load in the conventional system recover more or less in sync. But the issue is with this wind penetration. When we have a significant penetration of wind, one of the limitation of wind is its delayed post-fault active power recovery. So it's not going to come for various reasons. Several reasons. The active power from the wind following the fault clearance doesn't quickly pick up. So there is a delay in the recovery of the active power. As a result, since the load picks up quickly following the fault clearance, there is a temporary shortfall of generation and load due to this wind penetration. So this is the study that was done in the context of Irish system. Grid codes were implemented of the Irish TSO, and if you see on the right side with several penetration levels, the frequency fall is due to this is due to the fault and voltage fault, not outage of the generation. The fault, the voltage dip leads to the temporary shortfall of generation and load, which eventually leads the frequency event in the system. So in the worst case, this temporary shortfall can even exceed the largest feed in the system and may result in a significant frequency dip. So finally, the conclusion. High wind penetration for need for new emerging ancillary services that I try to highlight here is to consider, and I think while in India we are trying to catch up with the regular normal ancillary services, we should also consider to have a look at these new ancillary services that are already coming up in other countries. So these are the, for example, non-synchronous inertial response. I was talking, some of the countries are planning to have this as an ancillary services. Fast frequency reserve is again a bit different than the normal primary frequency reserve. It is a bit fast. And then dynamic reactive power and this post-fault active power recovery reserve is also some of the countries are considering to introduce in the market. Thank you.
Thank you, Professor Hussain. So 2 questions maybe.
Hello, Helge Oral from NSOE with background from GB. Thank you for a very interesting presentation. I'm particularly interested in avoiding Mustown in close to 100% operation, and particularly when you have 100% at a synchronous area rather than a smaller system area, very challenging. You mentioned the area of island, which is a separate synchronous area. I believe that the solutions you were talking about were very dangerous in context of frequency. Synthetic inertia with control based on DFDT, close to 100% has been proven from GB as making another stability issue much worse. The voltage stability at high frequency is dangerous above 2/3 of converter penetration. So we would suggest that that is a dangerous route to take. And at European level, we are now introducing, and GB is leading on that, moving to where Falk was talking about for having true voltage control rather than current control converters, which is being introduced in GB from 2021 in all areas. Have you looked at true voltage control to overcome many of these issues rather than continuing with phase-locked loops as we have done in the past? Thank you.
Thank you for the question. As far as emulated inertial response, as I talked about, so I was not intending to project this as a solution to the diminishing inertia. The intention was to highlight 2 issues that I was talking about: this maximum rock-off, which probably cannot be actually improved with emulated inertia, and second, I was trying to highlight the coordination of, if at all, wind turbines are going to participate in emulated inertia, the coordination between various wind turbines to avoid that next possible frequency dip due to the energy bouncing back after the event when they are trying to recover back to the normal speed. As far as the voltage control, dynamic voltage control, as I said, I gave the example is, for example, in Denmark, they are having the synchronous condensers. The synchronous condensers are not only providing the dynamic reactive power capability, they are also adding the inertia to the system, as well as short circuit power to the grid, which I was talking of, which is very important in the context of the protection schemes that we have in place in the system. So if we don't have a sufficient short circuit power following a fault, it can impact the protection schemes that we have in place. So we should have a sufficient dynamic reactive power and the short circuit capacity, short circuit power in the system. So one of the possible reasons which has been implemented in Denmark is these synchronous condensers. An interim solution, as I mentioned it, is these Mustown power plants that many countries are actually at the moment sticking to. In the meantime, they are trying to look at the long-term solutions. For example, in terms of, as I said, one of the new ancillary services that, for example, in Irish TSO is proposing is dynamic reactive power support in the grid. So it can be different, let us say, distributed generation, which is probably the synchronous or some other sources as well, whichever is capable of providing that dynamic reactive power. So it's a matter of how the TSO is planning. For example, Danish TSO took the path of having their own infrastructure in the system, while as many countries would probably go into the market, ancillary service market, and capture these reactive power capabilities to improve the voltage stability or voltage control of the system.
But can get all of those services cheaper by the converters themselves if you do true control.
Excuse me, I think we run out of time, so
Yeah, we can take maybe in the coffee break.
discuss
Further.
this after the coffee break. Thanks.
Thank you.